Assalamu alaikum students. So in this lecture we will talk about the two questions that is mentioned at the end of the ending slides. So the first one is you need to find out you need to calculate the pressure temperature diagram and pressure volume diagram, and similarly you can use the same process to find out the pure component properties. Okay. And then if you mix them together, then how you're able to find out uh, the properties for the mixed component. And on your right hand side you have some multiple components also mentioned. So what we will do is we will start with the pure component first, and then we'll go to the mixture, and then we go to the multiple components. So we'll start with a new simulation. Click on new case. The first thing you need to do is to select the components. So I will select all the multiple components in just in one list, and then we will keep on working with pure components, and then binary components, and then multiple components. So the first component on the list is water, second is nitrogen, third is hydrogen sulfide, fourth is carbon dioxide, then we have from methane to anhexane. So we select the first one, and then we keep pressing shift on the keyboard, and last component anhexane. So select the first one, keep pressing shift, and select the last one, and then add that component. So as I told you to select the, so now we only are left with C7 plus fractions. So the only thing which is as I told you before, you need to create the C7 plus fraction since it is not present inside Aspen HYSYS. So how you will create this one? You click on a pure component, change into a hypothetical component. Then you need to go on your right hand side and change from bash to just simple hypo. Then on your, so what we need to do is we need to select a new hypo from the list, just clicking on new hypo, and you can see here we have some dummy component that is created here. So all we need to do is we need to change the name, that is C7 plus. We are given the normal boiling point, which is 110 degrees Celsius. We can provide that one, and we have given the molecular weight is 111. We provide that one, and lastly we have the liquid density, which is in kg per meter cube, but here the default density units are pound per feet cube. So we can either change it from the list, or we can change it here also. So what we need to do is we need to select 741, and here you can see the drop down menu. Just click that one and change it into kg per meter cube. So what this do, basically this will convert 745 kg per meter cube in terms of pound per feet cube and put it here. Okay, now this is all we need to provide. The rest of the properties is not calculated, so what we need to do is we need to select the estimate unknown. So if you click on estimate unknown, the rest of the property will be estimated based on our given information. Okay, so once you do this, now the component is fully defined. You need to add this component, so select that component and click on add button. Okay, this will add the component in the list which is mentioned here. So now we need to select the fluid package. So in this case, because it's a gas, so we can select the Ping-Robinson equation of state, because Ping-Robinson equation of state is good for gases. Now we go to simulation environment. So in the simulation environment, we need to select the streams. We will select multiple streams based on how many components we have. So for example, if you are working with pure components, so the first stream we select, and we need to go inside, we change the name of this one into C1. Okay, since we don't provided the temperature and pressure, so we are working with the standard temperature and pressure conditions. So at standard temperature, the temperature will be 25 degrees Celsius, pressure is 1 atmospheric. So select that one. Since it is in bar, we need to convert into atmospheric. So we select the atmospheric from the list, and here you can select atmospheric. What this do is they convert 1 atmospheric into bar and put it here. Flow rate is not given, so we provide flow rate 100 kg mole per hour. Okay. Composition, since it is only a multiple, it is only so since we are only working with pure components, so it is only C1, so we will give only methane 1 overall composition, overall mole fraction, and click on OK. So once it is done, you can come to the you can close this one, and here if you look at here, we have this stream of C1 which is for the pure component is created. To find out the pressure temperature diagram, all you need to do is select that component, click on the right button, just right click and then go down, and when you see create stream analysis, click here and click on envelope. Once you select the envelope, you can see option here, select stream. So if you have multiple streams, you can select that. By default it is already selected C1, but if you have multiple streams inside your flow sheet, then you can have the option to change that one. So how you do this, just select the stream, select the multiple stream, which stream you want to analyze, and then you can click OK. But in this case only one single stream is mentioned, so just select that one and click on OK. Then you need to go on the performance tab, and you can see here the bubble point temperature respect to the pressure is mentioned in the form of a table. So at this pressure, this is your temperature, at this pressure, this is your temperature, and this pressure. So you can see here, as the pressure is increasing, the temperature is increasing. Similarly, you can click on the dew point and you can get the dew point tab. You can see here not much is changed because it is a pure component, and you know that pure component, both the bubble point and dew point is on the one straight line. Okay, what we are concerned with is the phase envelope or phase diagram. So for phase diagram, you need to click on the plot on your left hand side, and you can see here this is the pressure temperature diagram, or you can say vapor pressure diagram for the pure component, which is methane. So methane vapor pressure diagram or pressure temperature diagram. If you look at on the bottom of your right hand side, we have multiple options that is given. Since we are asked to calculate to find out the pressure temperature diagram, so this is the pressure temperature diagram. By default it is selecting pressure temperature diagram. If you want to find out pressure volume diagram, you can select pressure volume diagram, and you can get the pressure volume diagram on your screen. Okay, so now the second thing is what the question is asking, what is the critical temperature and critical pressure of the C1 and C2. So since we are working with the methane, you can get the critical temperature and critical pressure in either in this way, or you can find it inside the properties also. So if you click on the table and if you select, you cannot find from here, but you can go to the main design window. You can select the design window. You can see here the critical temperature and pressure is mentioned here. So the critical temperature of pure methane is -82.4 degrees Celsius, and the critical pressure is 46.41 bar. Even though they are also giving you some other extra properties for the phase envelope, which is creek on thumb bar and the creek on thumb bar pressure also. So both these properties are also mentioned. Okay, this is about pure methane. Same thing you can do for pure ethane, but in that case also what you need to do is you need to make a copy of this by copy and pasting, and change this one from C1, change the name from C1 to C2, and all you need to do is go to the composition tab, change the mole fraction from methane to ethane. Okay, put this one 0 and ethane 1, and then click on OK. Close this one. Now to find out the phase envelope for phase diagram for this one, all you need to do again is go right click, go to stream analysis, and click on phase envelope. Okay, you'll get this screen. Make sure this plot is not saved. So if you want to put this plot in your assignment or quizzes, you need to take the snapshot of the windows of the screen. Okay, again we need to select a stream. Since we have now in this case we have two streams, so we need to find out we want to analyze C2, so we select C2 and then click OK. We go to the performance tab. As always, it is shown in the form of a table, and we can also get the plot for this. Okay, so this is the plot for ethane, the pressure temperature diagram for ethane. Similarly, you can get the pressure volume diagram by clicking on pressure volume diagram. Okay, remember, as I told you before, you need to take a snapshot of this screen if you want to add this page on your assignment or quiz. Similarly, if you want to if it is asked to add the pressure temperature diagram on your assignment or quiz, you need to take the snapshot from the screen, and then you can add this one in your quiz or assignment, even in your exams. Okay, so this is pressure temperature diagram. So we done pure components. Similarly, critical temperature is mentioned, as I told you before, it is mentioned on the same plot. If you go again to the stream analysis and envelope, you can see here, if you click on the design tab, you can get the critical properties of ethane. Okay, so now we will move to binary components. So I will do only one, I will keep the rest of them for you to do. So let's do the first one, which is 60% C1 and 40% C2. Again, we need to copy paste the same because we don't want to key in the properties again and again. So what we do is just make a copy of this one, go inside, rename it into C2 C1-C2 because it is a binary components. We go to the composition, we change the mole fraction, we make it 0, this one first, then we will change. So 60% is ethane, so 0.6 is ethane, methane, and 0.4 is ethane. Overall it should be 1. Okay, click OK, close this one. Like always, go right click, go to the stream analysis, go to envelope, and you can see here we need to, since we are already created previous two streams, so we need to select the main stream which we want to analyze. So in this case we are analyzing C1 minus C2. You see here the binary components, which is C1 and C2. Click this one and we click OK. Then go to the performance tab. You will get all the data in the form of table for bubble point and dew point. Since it is an envelope, so you will see we have different dew point conditions and we have different bubble point information mentioned here. But what we are concerned with is we need to find out what is the plot. Okay, so we need to click on the plot. You can see here we don't get one line because it is a multiple components. This line is for methane and this line is for ethane, and it is coinciding at a point which is called critical temperature. Even you can see here when we are scrolling on the screen, I'm able to find out what is the temperature, dew point temperature and dew point pressure. Okay, so this is the phase envelope. If you want to find out pressure volume diagram, you click on pressure volume. You can get the pressure volume diagram. In this case, you can see the red line is bubble point line and this blue line is for dew point line. As I told you before, if you want to add this one in your assignment or quiz, you need to take the snapshot of this picture and then you need to add this one on your quiz or assignment. Okay, so this is regarding the binary components. So for other two parts, I will leave it to you. You will do by yourself in your house. Okay, do it as a practice. Now we need to consult with the multiple components. So for multiple components, again I need to make a copy of this. Since the conditions are same, only the components mole fraction is different, so I will change this one into I will call this one multi-component MC. Okay, I will go to the composition. This is the part which need to be changed mostly. The rest of the information will be same. I will keep this one 0 for the moment, and then I will start adding. So the first component on the list is water, which is 0. Second is nitrogen, which is 0.0001. We convert this into a mole fraction, then we are adding. Okay, 0.04778. Then we have 0.0071 for carbon dioxide. For methane we have 0.781. For 0.5. For ethane we have 0.0341. For propane we have 0.0592. Then for isobutane 0.0182, normal butane 0.0094, isopentane 0.0061, normal pentane 0.0077, and hexane 0.0123, and lastly we have C7 plus, which is 0.0164. So it is almost 1. So either we can normalize it, or you can normalize this whole mole fraction if it is given in the exam by mistake. It is not coming 1, and you want to make it 1, so we need to click on normalize. Okay, all this do is they will change the numbers in a way to make it 1. Then click on OK. Done. Now, as always, go right click, go to stream analysis, click on the phase envelope. We need to select the stream because we have multiple streams selected, so we select the required stream to analyze. We click on OK. Then we go to the performance tab, and you see here we have the information in tabular form, and for bubble point, and similarly the information of dew point in tabular form is mentioned here. We are concerned with the phase envelope, so we will click on the plot on your left hand side, and you can see here the plot is very much different than as it is shown with the binary components and the pure components. Why it is more fatter is because the more the component it has, and if it does contains heavy fractions, then like C7 plus fraction, then the diagram become a little bit fatter, and the region of two-phase region is become more and more. If you look at the binary component, like in previous case we have only two gases, C1 and C2, your diagram have a very small portion of mix, or small portion of the which contains both phases like inside, and your phase envelope is not very much fatter or thicker. But in this case you can see here the phase diagram is more thicker because we have multiple components, and we have some C7 plus fraction that will make or create the phase envelope a little bit fatter. Okay, so this is about this slide. We have pure components, and similarly you can find out the pressure volume diagram also. If you go to phase envelope again, and if you go to stream analysis and phase envelope, if you go to plots, and you can see on your bottom right hand side you have the option to select pressure volume diagram. If you select that one, you can have the option to generate pressure volume diagram also. Similarly, you can also create a temperature volume diagram and many other diagrams, temperature enthalpy diagrams. Okay, since we are only asked to find out pressure, temperature and pressure volume, so we are only concerned with these two diagrams. Okay, but you have the option to find out other diagrams also. Again, you want to add this one in your exam or in your quiz or in your assignments, you need to take the snapshot of this diagram, and then you add this one in your exams. Okay, so this is about this slide. Now, to find out the bubble point temperature, it is very much easy. Okay, for example, let's say you want to find out the bubble point temperature of C1. So if you open that one, by default it is given the standard temperature and pressure conditions. So to find out the bubble point pressure, all you need to know that for bubble point pressure, initially you have everything in the liquid form. Okay, your system has everything in the liquid form, and the point where the first bubble appears, that is your bubble point. Okay, bubble point temperature. So to find out bubble point temperature, first we need to do is we need to remove the temperature from this list, and we assume, or we are saying that we need to find out bubble point temperature. So for bubble point temperature is the point where the first bubble will appear, So initially it is in a liquid form. So when it is in a liquid form, you have no vapors. If you have no vapors and all is liquid, you put this one 0. So when you put this one 0, you can see here by default it is giving you this pressure. So let me remove this pressure also, because we need to find out bubble point at different pressure. Okay, so first thing you need to do is you need to provide the environment which states that you have the condition where everything is in the form of liquid. So when everything is a liquid, then the vapor fraction is 0. Now you need to find out the vapor, bubble point temperature at 6000 kilopascal. So 6000 kilopascal, you can directly put it here also. So you select here, put 6000, and from this bar you can select kilopascal. What this do again is to convert this kilopascal into bar and put it here. Okay, so you click this one. So you can see here for this particular what you call because since we are working with we are saying that it is a pure component, so at this condition there is no bubble point temperature available. So for pure components it is a little bit difficult to find out bubble point temperature and pressure and dew point temperature and pressure. So what we will do in that case, we will go to multiple components. Okay, because we know that multiple component does have a very vast range of bubble point and dew points. So again we go inside to the multiple components. We need to remove the two other properties which is mentioned, because we need to find out bubble point temperature. So the first thing we need to do is to keep the environment in a way that we don't have any liquid inside. We have everything. We don't have any vapor inside. So we put 0 for the vapor. For 6000 kilopascal, if you click here again and again you add 6000 kilopascal, you convert this into kilopascal, and you can see here at 6000 kilopascal, which is 60 bar, the bubble point temperature is minus 64.15. So the answer for this one is minus 64.15. Remember one thing, to find out bubble point temperature and pressure, it is mostly work with multiple components. So you need to go for multiple. So since we are selecting the multiple component stream, we are able to find out bubble point temperature at 6000 kilopascal or 60 bar. Similarly, dew point temperature you want to find out, again you need to remove this one. Okay, you need to remove this property, and then here for the dew point we are assuming that in the system we have everything in the form of a vapor. Then you need to find out temperature at the first drop of liquid form. So we are creating the environment, we have everything vapor, so this vapor fraction has to be 1. Okay, now to find out the dew point temperature what at 6000 kilopascal, again we need to do is we need to click on 6000, provide 6000 change into kilopascal, and this will give us the dew point temperature, which is 89.60. Okay, so this is how we can be able to find out the dew point temperature of the system, which contain multiple components. So I already done these two parts. Okay, the rest of the three, I think it will be very much easy for you to do also. All you need to do is instead of 6000 you need to go for 14,000, and here you have opposite, you need to find out dew point pressure instead of dew point temperature, so you need to provide the temperature. So this is for your home exercise, so I think you will be able to do this one in your home. Okay, that is regarding these two last slides which I talked about in the previous lecture, that we need to complete in the Aspen HYSYS in the next lecture. So I will finish this one. Okay, and the rest of them I think I leave it to you do it by yourself. Okay, so let's move to chapter number the next chapter, which is compressors. I will share this compressors chapter also on EduWave. Okay, so on Moodle, so you will be able to find out find this chapter in Moodle. Okay, so compressors as I told you before is opposite to liquid. pumps. What pumps are doing basically is they are used for liquid phases. But if you have gases in the system, then you don't use pump, you use compressors. This is particularly important when you're working with the simulation, which contains the simulation for the whole plant. So you need to check for different stream at different condition, what is the phase of that stream. For example, if the natural gas is flowing to a pipeline, the temperature and pressure you are providing at that particular stage is in a way that all the natural gas is converted into a liquid. Then you use pumps in that case. But if the natural gas phase is in a gas form, then obviously you use compressors. So finding compressors is also similar to simulating compressors is similar to pumps. The only thing is different in case of compressor is that it is used to compress the gas stream, not the liquid stream. So the compressor pressure is used to increase the pressure of the inlet gas stream. Depending on the information specified, the compressor calculates either a stream property, pressure, or temperature, or compression efficiency. Like previous case, we provide pressure and efficiency, they will calculate temperature. We provide temperature and efficiency, they will calculate pressure. Either or we can provide pressure and temperature and they will give us efficiency. Okay, so either way we can use. So after this, you are able to understand the learning outcome of this exercise is you are able to define the new hypothetical component, which this component, if you have a component which is not listed in Aspen HYSYS, and the only information you know about this component is the boiling point, then you can create a hypothetical component inside Aspen HYSYS and you can add that component in the list. Okay. Similarly, we will operate compressors using HYSYS and model the compressing process. Okay. And we will also study the compressor efficiency and the outlet temperature. What is the effect on changing the compressor efficiency or changing the outlet temperature on the compressor efficiency. Again, you need to go to Aspen HYSYS, open a new simulation. I will close this old simulation, close all case, and then open a new case. If you can see on my screen, I'm not closing the software, I'm just closing the cases. So this will helps you to do the next simulation easily and quickly. So the first thing we need to do is we need to select the component. If you look at on your screen, we have few components which is mentioned. Let me zoom this the screen. Okay, you can see here we have component list. So the first component we have in the list is methane, second is ethane, third is propane, then we have isobutane and normal butane, isopentane, normal pentane, and normal hexane. So all these components are in a proper order, so we can select all of them in just one single click. We select the first component and then we keep pressing shift and select the last component which is mentioned in the list, which is n-hexane, and then we can click on add button. Okay. Now the seventh component is C7 plus. We don't have that component in the list. We have only C7, but we don't have C7 plus fraction. How many pluses we have, we don't know. The only thing we know about this component is the boiling point. So we need to click on the pure component, change into hypothetical component, go on the right hand side and change it from batch to just normal. And on the bottom, we need to select just one hypo. We don't have the group of hypos, we have only one hypo component, hypothetical component. We click on one hypo. We can give this one a name, C7 plus, and the only thing we have for this component is the boiling point. If I go down, you can see here the only thing we have for this component is the boiling point. We can select that one and provide the boiling point, which is 110 degrees Celsius. We don't have the other properties, so to find out the other properties, all we need to do is click on estimate unknown, and this will create the other properties based on the boiling point. Okay. The accuracy of this component depends on the properties. The more the properties you will give, the more accurate is the properties of this, the rest of the properties of this component. However, we only have one property, which is the normal boiling point. Based on this property, he is estimating the other properties of the component. We already find out other properties of this component. Now we need to add this component in the list. So select that component and add it. Make sure you need to, don't forget to add the fluid package. We will select Ping Robinson since it is a gas, and the Ping Robinson is good for gases. So we select Ping Robinson and then we go to simulation environment. And like always, the first thing you need to do, is you need to provide the material stream. Select the material stream and then open this stream and call this one. You can leave it like this also, but you can call this one feed. The temperature for this one is 100 degrees, or you can call this one natural gas. Okay, but I'll call this natural gas. The temperature for this one is 100 degrees Celsius, which is mentioned here. Pressure is 1 bar, and the molar flow rate is 100 kmol per hour. Composition is mentioned here. You can key in the composition one by one. For ethane, we have 0.330, ethane 0.143, propane 0.101, isobutane 0.098, normal butane 0.080, and 0.069, 0.059, 0.078, 0.042, and then enter. So altogether it has to come 1. Otherwise you will normalize, or you will check the composition first, and then if it is correct as given in the exam, then you need to normalize it if it is not correct. Okay, click OK and click close. So we fully define this stream. The second thing we need to do is we need to add a compressor. If you go to your model palette, you can see we have compressors mentioned here. Okay, this one, even just scroll it on the top, you can see the name compressor. Click on the compressor and put it in the center. Then double click. You have, just like pump, you have the name, the inlet, the energy stream, the outlet. So I will call this one a compressor. You can leave it like this also, but I will just call it compressor. The inlet we already have, which is natural gas stream. Outlet we did not create. We can call this one comp out. Okay. For energy stream, we can call this one, call the energy stream work. Okay, fine. Now in order to simulate the compressor, what we need to do first is, since we are given some different efficiency, so what we need to do is we need to change the efficiency from 75 to 30%. This is called adiabatic efficiency. Then we need to, since to simulate this one, we need to provide one information for the exit stream. So we need to click on the worksheet and we need to go on to the outlet stream, and what information we have for the outlet is the pressure, which is 5 bar. So what we are doing is we are increasing the pressure from 1 bar, or we are compressing it to 5 bar. Once we provide that information, you can see here, based on our efficiency, which is mentioned in the properties window, which is 30%, and based on the pressure, they calculate the temperature, which is 265.8 degrees Celsius. Okay, so this is the answer for this question. What is the outlet temperature? Which is 265.8 degrees Celsius. So this is the end of this problem. You can save the simulation by clicking on the same save tab, and then you can save it anywhere on your screen. Make sure it is a HYSYS simulation cases file. Okay, HSC file format. If it is that format, it will be the right format. Okay, now The discussion part: the compressor has only 30% efficient and causes 165.3 degrees Celsius increase in temperature of the natural gas. The less efficient compressor is the greater the increase in temperature of the gases will be. So you can see here, the less efficient is the compressor efficiency, the more the temperature it will generate. So now we need to do some further study. So in further study, they will give you the temperature for the outlet stream, and indirectly there you're asking you to calculate the efficiency. To calculate the efficiency, what you need to do is you need to go to the outlet stream and you need to delete this pressure that you given previously. Again, you go back to the compressor, and if you go to the design and properties, you need to remove that one also, because you need to calculate the efficiency directly. Again, go back. Since the pressure has not changed, we keep the pressure 5 bar, and the temperature that is mentioned in the question is 400 degrees Celsius, so we provide 400 degrees Celsius here. So based on our conditions, provided condition, they will calculate the efficiency. To find out where the efficiency is, just go inside the compressor, go to the parameter, and you can see the efficiency is mentioned here, which is 14.944. To display the efficiency, all you need to do is select the component, right click and show table. Since efficiency is not shown by default, you need to add that one manually. So remove the other variables which is not required and add the adiabatic efficiency which is mentioned on the top. Add that one, click done, close it. You can see the efficiency is mentioned here. So this is the end of this exercise. You can even do case study for this one by providing different temperatures and wanted to see what is the effect of adding different temperature on adiabatic efficiency. Again, this is your home exercise, so I will suggest you to find out the case study. In the case study, what you need to find out is what is the effect of changing the temperature of the outlet stream on the efficiency of the compressor, or changing the efficiency of the compressor on the outlet temperature. So this is your home task. Hope everything is clear, and hope you don't have any problem simulating compressor in HYSYS. Okay, if you have any questions, please don't hesitate to ask. Thank you very much for listening to me. Take care and bye.